In this short video, I'll be explaining the kinetics experiment involving crystal violet and sodium hydroxide. The reaction is shown here. An aqueous solution of crystal violet is dark purple, and sodium hydroxide, of course, is colorless. And they react to produce a colorless complex that's shown on the right side of the equation. Now, the reaction is not immediate. It takes a few minutes, which is useful because we can take advantage of this to measure the rate of the reaction in this kinetics experiment. Here is the equipment we'll be using. I'm using a Pascho PS2600 spectrometer and tablet. You'll need a solution of crystal violet of known concentration and sodium hydroxide of known concentration, and a stopwatch. We are using 1 centimeter plastic cuvettes. In part A of this experiment, we'll be measuring the wavelength of maximum absorbance of a crystal violet solution. It's called lambda max. So for this, you do not want to add sodium hydroxide, only crystal violet of a known concentration. You'll be using the analyze solution mode, and that's the top left tile in the menu bar that you see on the tablet. In that mode, the absorbance is shown on the y-axis and the wavelength on the x-axis. And in the picture you can see that the highest absorbance occurs at an x value or wavelength of 587 nanometers, and the absorbance value that's read from the y-axis is shown to be 0.67 absorbance units. So using that absorbance and the known concentration, you can calculate the molar absorptivity of crystal violet, and that's explained in the lab procedure and by your instructor. In parts B and C of this experiment, you'll be working in the time mode, which is the tile that is third from the left in the top menu bar of the tablet. And in this mode, you'll be combining crystal violet and sodium hydroxide, and the color will fade. The y-axis of the plot is still absorbance, but the x-axis will now be time, and you'll see the absorbance declining over time. First, you add the crystal violet solution, and you can take as much time as you need to do that, so you can deliver the required volume with a Mohr pipette or a serological pipette, any graduated pipette. But then the sodium hydroxide is added second, and it needs to be added quickly, because as soon as it's added, the reaction begins, so you don't want to be waiting for the pipette to drain the sodium hydroxide. So for that second solution of sodium hydroxide, you'll want to add it either with, say for example, a serological pipette that is loaded with the correct amount in the bottom, and you can blow that volume out carefully and quickly with a bulb, or preferably, and what I did is used a auto pipette to deliver the required mils of sodium hydroxide, and that gets the solutions together and mixed quickly. As soon as I add the sodium hydroxide, even before I mix it, I start the timer. Your partner can do that immediately as you add the sodium hydroxide. And then I used a piece of parafilm on top of the cuvette, inverted it a few times, as you'll see in just a moment, and quickly put it in the spectrophotometer, and I started recording exactly at the 10-second mark on the timer. So it does take 5 to 7 or 8 seconds to mix the solution and get it in the spectrophotometer. I waited to the 10-second mark to start the record button on the instrument. And the reason I did that is it's an easy number, 10 seconds. I can easily add that to all my time readings later on when I want to interpret the values. To start the recording at the 10-second mark, you want to press the record button, which is the small red circular button in the lower left corner of the screen. Immediately after I pressed the record button, I also pressed the zoom full screen button, so it will show the entire plot on one screen. So let me show you what this looks like, and I'll explain a little more once we're underway here. So here for part B, I'm adding 1.5 mils of 2E minus 5 molar crystal violet. You can take as much time as you need to do that. Now I'm going to change the tip on the pipette so I don't mix my solutions. I'm going to add 1.5 mils of sodium hydroxide. And as soon as I add that sodium hydroxide, I'm going to start that timer immediately. Your partner can press the timer as you add this right now. Now I'm going to mix that 3 or 4 times, quick as I can, and put it in the spectrophotometer, and then I press the record button right at the 10-second mark. Wait exactly to 10 seconds, I was real close, followed by the zoom full screen button, and that'll record absorbance versus time and fit it on the screen. Now you want to wait 300 seconds. The plot is time and absorbance. Notice that the circular red record button changes to a square red stop record button. Now I'm going to speed this up, and at the end of 300 seconds I'll explain further what you're to do with the data. After you have stopped the recording, you want to press the linear fit button. It's the 4th tile from the left in the lower menu bar of the tablet. When you press that button, the spectrometer will try and fit a straight line as best it can to your data. And the image here, you can see absorbance versus time does not follow a straight line, and the goodness of fit is evaluated by what's called the Pearson correlation coefficient. It's an R value. You see in this image it's negative 0.983. It doesn't matter whether it's positive or negative. The closer it is to a magnitude of 1, then the better is the fit between the line of best fit that you apply and the actual data. In this case, it's not a very good fit. If it was a good fit, if this was the best fit, it would suggest that the rate of decay is constant and it's a 0-order reaction. But it doesn't look like it. The spectrometer will give you other plots. So on the y-axis above the absorbance label, you'll see a small blue and white icon. Looks like a calculator. It's called the Quick Calcs button. When you press that, it will display the data. This time it's the ln of the absorbance rather than absorbance versus time. And you'll also see the line of best fit, the straight line of best fit, fits very closely. They're almost superimposed. And in this case, the R value is negative 0.999. It's almost a perfect fit. And when ln of absorbance versus time is linear, it would suggest, in fact, that the relationship between crystal violet and its decay, the decay rate of crystal violet, is first order kinetics. And that looks pretty good. But let's take a picture of each of these as you obtain them for your lab report. And the third option you have, if you again choose the Quick Calcs button, you'll get a plot of the inverse 1 over absorbance versus time. And again, a straight line you can see does not fit very well. The R value is positive 0.963. Its absolute value is not very close to 1. If this did fit the best, it would suggest this is a second order kinetics reaction with respect to the concentration of crystal violet decay. So that's really all there is to Part B. Make sure you take snapshots or photographs of each of these images for your lab report. Now Part C is done very much like Part B. You'll be combining fixed ratios of crystal violet and sodium hydroxide. You'll be working in the time mode and recording absorbance versus time, but you'll be doing replicate runs with different ratios of crystal violet to sodium hydroxide. And in Part C, you'll be varying the concentration of sodium hydroxide. And then you'll be able to determine the order of the reaction with respect to the hydroxide ion. You'll need to refer to the procedure and your instructor for doing that. These runs are only 60 seconds long because you'll be measuring the initial rate. And I think that's probably sufficient to get you started. All the best.